Last time we were talking about obtaining the density of states for a free electron in a particle, or we were talking about were conduction electrons in a solid. We calculated the density of states to look like this, and notice that first, the density of states is proportional to the square root of the energy for a dimensionless, I should say, a three-dimensional box of free particles. If you want to know how many states were to lie between two energies, let's say E1 and E2, what this is telling us is all I have to do is integrate the density of states between those two energies, and that will tell me what the number of states is. The rule of thumb here is that density of states is a quantity that lives to be integrated. It always is integrated whenever you use it. So in this case, for a free electron gas at T equals 0, we get a total number of electrons by integrating up to the Fermi energy. So all we would have to do then is say n is equal to the integral g of E dE from 0 to the Fermi energy. Suppose, though, we want to look at a case when T is not 0. So if T isn't 0, what we do is we multiply g of E by the probability of a state with that energy being occupied. In other words, by the Fermi-Dirac distribution. So we can say n is equal to integral 0 to E sub f g of E n fd, the Fermi-Dirac distribution of E dE. And I can write this as 0 to infinity g of E dE over e to the E minus mu over kt, or times beta, however you like, plus 1 for any temperature. The energy then I can write as 0 to infinity E times g of E n Fermi-Dirac of E dE. And that will work for any temperature as well. So I can write this as integral 0 to infinity E g of E dE over the distribution E to the E minus mu over kt plus 1. So this works for any temperature. Remember that the chemical potential at any temperature is not equal to the Fermi energy, except when we're at 0 kelvins. Let's look at some more interesting applications of the Fermi-Dirac distribution. We can do the following. Let's look at white dwarf stars. White dwarf stars have masses on the order of the sun, so mass on the order of, let's say, 2 times 10 to the 30th kilograms, but have radii on the order of the Earth. About 1% of the sun, just for argument, radius of the dwarf is on the order of, let's say, 7 times 10 to the 6th meters. A little bigger than the Earth. Now the density of the sun is about 1,000 kilograms per cubic meter, similar to the density of water on Earth. The density of the dwarf, however, is more like 10 to the 7 to 10 to the 10 kilograms per cubic meter, so it's extremely dense. Atoms are completely ionized into nuclei and free electrons, and the electrons form a degenerate gas. We call it a degenerate electron gas, and it keeps the white dwarf from collapsing. Now, we can define this, even though white dwarfs are rather hot, we can talk about this gas as being at a very low temperature. For example, let's talk about probably the first white dwarf discovered was Sirius B. That's the companion to the very bright Sirius A. Sirius B is a white dwarf. The way it was discovered was the fact that it caused the orbit of Sirius A to oscillate just slightly, which led astronomers to conclude that Sirius A had a companion that they just couldn't see. By orbit measurements, the mass of Sirius B was on the order of 2 times 10 to the 30th kilogram. So it's the same mass as the sun. But the radius of Sirius B was on the order of 2 times 10 to the 7 meters, so just slightly larger than the Earth. So the density, of course, is just the mass over the volume, which is going to be something like 6 times 10 to the 7 kilograms per cubic meter. At this density, all the electrons are ionized and form an electron gas. The matter in white dwarfs is held together by gravitational attraction. It is this pressure, this degeneracy pressure, that pushes outwards against the gravitational pressure that holds the white dwarf, keeps it from collapsing or expanding. So, generally speaking, we can say that KT is much, much less than the Fermi energy. We can calculate the Fermi energy. That's just h bar squared over 2m 3 pi squared n to the 2/3, and that's going to be on the order of 5 times 10 to the minus 14 joules, or if you like, 3 times 10 to the 5th electron volts. That's about 10 to the 5th higher than a typical metal. Fermi temperature then is going to be on the order of 3 times 10 to the 9 kelvins. The actual temperature inside the dwarf is about 10 to the 7th kelvins, so the thermal energy of the electron gas is much, much less than the Fermi energy. The question becomes, are electron energies relativistic in this case? Well, up to now, we've used just classical expression for kinetic energy, p squared over 2m. But for rest mass energy on the order of mc squared, where we're getting that 1 times 10 to the minus 13 joules, that's on the order of the Fermi energy. So relativistic effects in white dwarfs will be significant, but they won't be dominant. Let's take it a step further. A star, and we'll do this calculation, by the way. A star that exceeds 1.4 solar masses after it's blown its outer layers off can't be a white dwarf. It's going to collapse too far, and its ultimate fate will either be that it will be a neutron star or it will become a black hole. So we'd like to look at neutron stars, which is to say, instead of having degenerate electrons, you have degenerate neutrons. But before we do, let's talk about nuclear matter in general. So neutrons and protons can form highly degenerate gases, fermion gases or Fermi gases. Let's look at the Fermi energy in that case. So the radius of a nucleon or a nuclei is on the order of 1.3 times 10 to the minus 15 meters times the atomic mass to the 1/3. That's a pretty good approximate. Atomic mass gives us the number of nucleons. So the concentration of nucleons in nuclear matter then is about A divided by 4 pi times the radius cubed, 1.3 times 10 to the minus 15 cubed, which is on the order of about 0.11 times 10 to the 41 of these per cubic meter. So that's about 10 to the 8th times higher than nucleons in a white dwarf by comparison. So this is very, very dense. Now, the Fermi energy of protons is not necessarily the Fermi energy of neutrons, but for this case, let's assume they're about the same. Fermi energy, I can write as h bar squared over 2m, 3 pi squared n, 2/3. And n is the number of protons or neutrons, whatever the case may be. Put all my numbers in, I'm going to get something on the order of 27 MeV. So the average kinetic energy of a particle in a degenerate Fermi gas is 3/5 times the Fermi energy. So in nuclear matter, the average kinetic energy is about 16 MeV per nucleon. That's pretty interesting. It becomes more interesting, though, to look at conditions where we have to take relativistic effects into account. And what I'd like to do is look at 3 examples. 2 for the case of neutron star, white dwarfs, and 1 for the case of neutron stars. First example I'd like to do is to consider a case where you have a degenerate gas where all the electrons are highly relativistic. So in this case, highly relativistic means my energies are much, much larger than mc squared. So I can write my energy as, instead of p squared over 2, I'm going to write it as pc. And so what I want to do is determine the chemical potential for this kind of case. It's going to be different than the way we did it before for non-relativistic particles. We're going to allow wavelengths lambda x be 2L over n sub x. Momenta would be p sub x, and they're going to be n sub x h over 2L as before. Py similarly, and y h over 2L. Pz and z h over 2L. But my energy, I've got to write it differently now. My energy is going to be written as hc over 2L square root nx squared plus ny squared plus nz squared. HCN over 2L. Once again, we only need to consider 1/8 of the sphere, since all the n's are squared, and that will cover all possible different single particle states. So I can write n is equal to 2 for spin times 1/8 times 4/3 pi n squared max, which I can write as pi n cubed max divided by 3. So then n max is equal to 3n over pi to the 1/3. My chemical potential is equal to my Fermi energy is equal to E max in this case, E for N max, I should say. That's going to be HC over 2L, 3N over pi to the 1/3. That's going to be HC over 2, 3N over pi times v to the 1/3. And that is my chemical potential for a relativistic degenerate gas. How about the energy? The energy is going to be equal to the sum over nx, ny, nz. 2 for spin. I can write this as 2 d phi, d theta sine theta, as we did before, dn n squared hcn over 2l, from 0 to n max, 0 to pi on 2, 0 to pi on 2. I play all that through, and I'm going to get 3/4 n times the Fermi energy. So this is a real difference. What we found, the average energy for a non-relativistic degenerate gas was 3/5 times n times the Fermi energy. What we found this time is it's 3/4. Very interesting. Interesting difference between the two. Okay, as promised, we've got a couple of examples left. And I want to do one for a white dwarf star and one for a neutron star. And these are both relativistic problems, but again, using applications of the Fermi-Dirac distribution. And with the problem that we just did. So for a white dwarf star, we've got carbon nuclei, we've got degenerate electrons. We're going to model it as a uniformly dense sphere. And while we know they're hot, we can still model it as a Fermi gas at T equals 0 and still come up with some pretty good answers. Let's first come up with an expression for the gravitational potential energy. In other words, what's the potential energy, or the energy to configure by gravity, a sphere of constant density rho, radius r. Let's start with a sphere of radius r and a mass equal to rho times 4/3 pi r cubed. Okay? And what we're going to do, we're going to configure this white dwarf. White dwarf. We're going to configure this white dwarf by bringing shells of mass in. Concentric shells of mass. Each shell will have a mass dm. It will have a thickness dr, such that I can write dm as 4/3 pi r squared dr. Okay? 4 pi r squared, okay, the derivative. 4 pi r squared dr. Okay. So my gravitational potential energy is going to be integral of du, which I can write as minus integral of g m over r dr, good old classical physics. G m over r, dm, sorry. Write this as minus g integral 0 to r of 1 over r 4/3 pi r cubed rho 4 pi r squared rho dr. I'm putting my volume element. Compute that all through, and I get that my gravitational potential is minus 16 pi squared g rho squared r to the 5th over 15. Of course, rho is equal to the total mass divided by the volume, 4/3 pi r cubed. So I can write my gravitational potential then as minus 3/5 g m squared over r. Okay? So that's my gravitational potential for the white dwarf. How about the kinetic energy? Kinetic energy with degenerate electrons, I can write that as 3/5 n times the Fermi energy, which is going to be 3/5 n h bar squared over 8mc, 8m times mass of an electron, 3n over pi v to the 2/3. N is equal to mass divided by 2 times the mass of a proton. We'll let protons and neutrons have the same mass. No harm with that. They're close. V is equal to 4/3 pi capital R cubed. Put all those values in for kinetic energy, and we're going to get something like 0.0088 h squared m to the 5/3. Mass of the proton to the 5/3, mass of the electron, r squared for kinetic energy. Equilibrium radius for the dwarf would be that radius that minimizes the total energy. That is to say, that if I sum the gravitational energy and the kinetic energy, can we find an equation for the radius in terms of the mass? Well, this takes some hand waving. I know that the gravitational potential goes as -1 over r. I know the kinetic energy, looking at that, goes as 1 over r squared. So to find a minimum for the total energy, we might do something like this. Set the derivative equal to 0. We can say 0 is equal to the derivative with respect to r of minus some constant over r for the potential plus another constant over r squared for the kinetic term. And if I do that, I find that at equilibrium, I solve this, I find that r is equal to 2 beta over alpha. And that's going to give me, put all my variables in, that's 2 times 0.0088 h squared m to the 5/3 over mass of the electron, mass of the proton to the 5/3 divided by 3/5 g m squared. So that would be my equilibrium radius for the dwarf. So for a 1 solar mass white dwarf, I put the numbers in. 1 solar mass white dwarf, that's 2 times 10 to the 30th kilograms. That will give me a radius on the order of 7,200 kilometers, slightly larger than the Earth. I can also calculate my Fermi energy. I can calculate my Fermi temperature as well. Temperature is just going to be the Fermi energy divided by the Boltzmann constant. Fermi energy is just going to be h squared over 8 times the mass of the electron, 3n over pi v to the 2/3. And that's going to turn out to be something like 0.19 MeV, which gives me a Fermi temperature of about 2.3 times 10 to the 9 kelvins. If the electrons are ultra-relativistic, my kinetic energy term has to change because I have to use a different Fermi energy. What I find then is that my kinetic energy is going to be proportional to 1 over r. This is a disaster because when I try to minimize to find the radius of the star, I have a 1 over r here and a -1 over r for my potential energy. Now I have an unstable minimum for the total energy. So in the case of an ultra-relativistic term, I'm not going to be able to solve this in the usual way. Let's do this next time.